Everybody good? Okay, elimination. Leaving group chemistry. We can substitute leaving group. We can also eliminate. Now, the elimination refers to the overall reaction. We take a compound and we can just eliminate something. We're not adding anything. That would be an addition reaction. We're not replacing anything. That would be a substitution. We're eliminating. So we have a general line reaction here. This alkyl halide, the leaving group. We have this here, which can be a nucleophile, but it can also be a base. Okay? And we can do what we're going to call a beta elimination, and we're going to eliminate, because if you take this and you look at this product here, what have we done to this?
Turn it into an alkene.
We've removed an H and a bromine. We've eliminated an H and a bromine. We didn't add an H and a bromine. We didn't replace the bromine with something. We removed an H and a Br. Sometimes you can write this as, okay, what did we remove? Minus HBr. Everybody agree we removed an H and a Br from this? Okay. Did we actually generate HBr? No, but we removed HBr. So that can be kind of the terminology we can use. And elimination reactions typically give pi bonds, and for the introductory, usually it's alkenes. Okay. And so we remove the leaving group. We would also remove an H here, right? Because the middle carbon only has one H. There's two here. It's called beta elimination. That refers to the H that's being removed. From the leaving group, or from here, that's the alpha carbon, beta carbon. So we're removing a beta hydrogen in this reaction. That's why the term beta elimination is used. Beta refers to where the H was. Okay, two possible mechanisms, just like I did for substitution, SN1 and SN2. Here we'll do E1 and E2, and then ask, well, which one is the best mechanism? Okay. The leaving group has to leave. We could just have it ionized, right? We've done that before. That would give this plus what?
Br minus.
Br minus. Now, perhaps you're already not liking this mechanism. Who's not liking it? Why? Primary cation bad. Okay? All right? But we're going to do it anyway because it's going to be an SN1. What's the first step? I'm sorry, an E1. What's the first step of an SN1? The same thing. The first step of SN1 and E1 is the same. Leaving group leaving, ionization. Okay? What can happen next? This thing, what do we have to do? We got to remove the beta hydrogen. At this point, this can act as a base, come in and take the H, and then these two electrons can just sort of fall in and make pi bond. That's what these arrows mean here. What does this give? We're done. It gives all that. You can draw an arrow to that. Okay? Because the alcohol on the far right is made right here, correct? And when this moves in to make pi bond, what do you get? You get that. I'm showing a two-step mechanism. The first step was, well, which step appears to be rate determining?
First step.
Yes, first step. Forming the carbon, just like SN1. Ionization is going to be the rate determining step. This is going to be thus a fast step. Now sometimes you can get specific and say that this here is the beta elimination. You need to go through each step and give each various lingo to it. For example, we can say, okay, how else can we describe the first step? What about this? Algae leaving? Is that a way we can describe it?
Yes.
Many ways to describe it. You should go through and practice that. How else can I describe this?
Carbocation being formed?
Do what?
Carbocation forming?
Right. You could list 10 different things that are going on in that first step. Leaving group leaving. May not be as short here, but removing the beta H. Isn't that what we're doing in the second step? What else are we doing in the second step? Putting in the pi bond. So this will all be the lingo that I will use. And when I say this, I mean you got to know what's going on in each step. Okay?
Dr. Stevens,
Yes.
why does the electron pair attack the hydrogen as a positive charge?
You want to attack the positive charge? Reasonable. Let's attack the positive charge. Bam, what would that give? Oxygen bonding to the N carbon would give this. Okay. There you go. Let's say that product was formed. If that product was formed from this, is that an elimination product? What type of product is that? It looks like it used to be a bromine bonded here, bromine under the hand, but now there's an oxygen. That's a substitution reaction. And you know two mechanisms for substitution, SN1 or 2. If we did that, would that be SN1 or 2?
SN1.
SN1. Who has a problem with that? Why?
The primary carbon should it be a
Yeah, well, we got to get past that. It is primary, so yes. But what's another reason it's not SN1?
it's an anion.
It's a strong nucleophile. If this was SN1, is that nucleophile going to lead to SN1? It's strong. Strong nucleophiles are bullies. I'm going to stick my, here I come, backside attack. It'll be SN2. So you got problems. In the end, we're going to say substitution and elimination often compete. You could do either sometimes. You could do either sometimes. I'm doing elimination because this is what we're doing right now. Yes. There's an option. Instead of attacking here, you get a substitution product. We're removing a beta hydrogen, putting in pi bond, and that's an elimination product compared to what we started with. Okay, I'm not liking that mechanism, but that is an E1. Ionization is a rate determining step. Then fast beta elimination generate alkenes. Yeah, that's what we said, right? Let's try another mechanism, E2. By the way, how many of these reactants was involved in this rate determining step? One. Was this thing involved in the rate determining step in the mechanism we did?
No.
No, that's why it's not E2. It's only E1. Let's try E2. Well, someone suggested another mechanism. Anything. Doesn't have to ultimately be E2, but how else could we do this to get these problems? You can't say you're going to start with bromine disleaving because that would be what we already did.
Because of the infection, or because of the protein, it pulled the electrons so that part is positive, partially positive.
Certainly, we always have a dipole here.
And so the electrons from the other molecule would take, like with the attack, backside attack,
Attack the carbon. This attacking this carbon? I mean, we could. Is that going to give us? That looks like it's going to give us substitution. That looks like SN2. I mean, You're proposing to have oxygen bonding to this carbon instead of bromine? I mean, that's not going to give us the alkene.
Would the oxygen attack the beta hydrogen?
Well, ultimately,
found-
you got to see what you're going to form. Yes, the oxygen now has an H. Ultimately, it is somehow bonded to an H. We got all those products before one way. What I'm asking is, can we get all those products some other mechanistic way? Don't sit like this, look like you're raising your hand. No?
Never mind. I was gonna say, is it the backbone, but there's no carbocation.
Uh-huh. Okay, it's all concerted now. Another mechanism is, what if this bonded to an H, these moved in here, and those got kicked off then? What would all that give?
The product?
You're done. Yes. There you go. There you go. I underlined the word there, concerted. What does concerted mean? All at the same time. We actually had some concerted nature in the first mechanism. When I took the H and the electrons moved in, kind of concerted. But this is everything's concerted. There you go, there's your mechanism. Okay, which step is the rate determining step?
The only step?
That step. I only showed one step. Okay? Yes. It's only one step. It's all concerted. Are both substrates involved in that step?
Yes.
They better be. I mean, it's only one step. If they're reacting, they got to be involved. Yes. So did we do an elimination? Yes. Bimolecular, two involved. E2. And E2 is a concerted beta elimination with no carbocation. Did we form a carbocation here? Where's it at? No. But E1 had a carbocation. What about, okay, E1 has a carbocation, so does SN1. E2 does not. What about SN2? Does SN2 involve carbocation? No. E2 and SN2 don't involve carbocations. But SN1 and E1 do. Those have the same first step, forming the carbocation. Okay? Rate determining step, E2. Questions about this mechanism? Does this look reasonable? Do you have any questions about it? Concerns? I would think there'd be a concern about something there. Or you just want to take it as fact? I would recommend you question things that you don't think look reasonable.
Do you have to have heat in that one too, like the SN2s, or is it different?
Heat probably. I'm not sort of giving you all the fine details. We'll talk about, SN2 and E2, because they're bimolecular, because the rate determining step is bimolecular. Heat is often kind of helps more. Because you got to get two molecules to come together in that hard rate determining step. Yeah. Other questions? I was wondering, why did someone not ask, why would this grab that H? Is that H acidic?
No.
Okay. No, it's not acidic. I mean, if 2 months ago we looked at this here, would you say that H is acidic? No. The H that's being taken is not acidic. So how are you taking it? Well, that would be a great question. But it is all concerted because we really didn't do an acid-base reaction. Did we? And I can move to the next page, I think. Another possible mechanism. Okay, that was E2. Any other possible mechanism? Let's do this a third way. Not one of the same ways, but a different way. What if this took this and these electrons just went there? What would that generate on this here?
Carbon.
Yes. Did we do this in one of the two previous mechanisms? No. This is a third possibility that I'm showing. Then, because that right there would give the alcohol, right? Now from here, how could we get the alkene and the Br minus? Now these electrons could move in and kick off the leaving group. How about this? What would that give? It would give all products, right? Is that a third mechanism, or is that the same as one of the previous ones? That doesn't look like one of the previous ones.
It's different.
Third one. This is where you treat the H as a traditional acid proton, and you remove it and make the anion. But guess what? It ain't acidic. And you ain't doing that. Removing the H is not a traditional acid-base reaction because it ain't acidic. Sometimes students, that is, you guys will kind of maybe want to show something like this. No. The choices for elimination of a leaving group from a tetrahedral carbon are either E1 or E2 in this class. This may apply sometimes, but only if the H is acidic. And never in this class will it be acidic. What I'm telling you is, never do this third mechanism in this class. Okay? But it's worth looking at and seeing a third approach and recognizing that the approaches that we are doing, we're not doing a traditional acid-base reaction to begin with. Okay, mechanistic questions. This should be pretty easy when they've already asked them. In which elimination mechanism does the leaving group leave the returning step? Real quick. E1 or E2?
Two. Both.
In which does the leaving group leave the returning step?
Both.
Both, yes, good answer. And which elimination mechanism is the beta hydrogen abstracted in the rate returning step?
Both. Abstracted?
No, not both in this case.
What is abstracted?
In which mechanism is the beta hydrogen removed
Oh,
in the rate returning step? Only E2. In E1, it's removed in the fast step, right? Okay, these are the types of questions you need to know. All right, let's look at a next example here. If you take this alkyl bromide and just heat it in a neutral alcohol solvent, or no solvent at all, you just take that alkyl bromide and heat it, you can get those products over there. What type of reaction occurred? Substitution, elimination, rearrangement? Elimination. Okay? And when you eliminate, you convert one molecule into two. Because you eliminate something, you remove something. Okay? And here we eliminated HBr. And in this case, it's actually going to form. All right? Mechanism here. Is this SN1 or SN2?
not SN.
It's not SN.
It's an E1.
What about the base, the thing that takes the H? Is it involved in the rate determining step? I mean, which mechanism is it involved in the rate determining step?
E2.
E2. Okay. Well, just like with SN2, when you do an E2, the base needs to be strong. Okay? The other thing, not the leaving group thing, but the other thing, either the nucleophile or the base, for it to be bimolecular reaction, that is SN2 or E2, that thing has to be strong. Okay? Now, elimination, we call it a base because it takes an H. Do you consider this a strong base?
No.
It's the same consideration as nucleophile. What are strong bases? Anions, sp3 nitrogen. And we'll talk about some subtle differences. That's not a strong base. It can't do E2. This is E1. Since it's E1, what's the mechanism?
Leaving group.
Yeah, you heat this thing up, and that'll just get this thing to ionize. And that leads to that plus Br minus. Okay? With heat, leaving groups can just be made to ionize. Always? No. We don't want to form a primary carbocation. What type do we form here? Secondary. Is secondary okay?
Yes.
Yeah, it's okay. It's not going to form as easily as a tertiary carbocation. But it's okay.
What if we didn't have that methyl group coming down and it was then primary, would it still happen that way?
It's the same.
According to what we've said, I would say no, because we've said we don't want to form primary carbocation.
Okay.
It would certainly be much more difficult, and I would suggest it's probably not going to happen. That is, if you heat that compound, nothing will happen. If you heat this compound, something will. So we can say that this compound is less stable to heat because something's going to happen. It can ionize, and at this point, what can happen? This can add as a nucleophile, but it wouldn't get that. If it's possible to do that, what else could happen? Well, what if this came back and took the H and these moved in? What would that give? That'd give the alkene. Plus what? What else did we form? HBr. And if we do this, do you even need a solvent?
No.
You could actually do this with no solvent. So you see how just heating one molecule could lead to elimination or decomposition. The molecule broke down and did something. Okay? What about stereochemistry? My product is trans. This looks kind of cis. How did we go from that?
Because it can turn the nuclear
Because what?
carbocation. Once that has that carbocation, there's not a pi bond there, so it can rotate, right?
Very good.
And then it'll
Yes. Do molecules rotate? Is it reasonable to expect that this might rotate? Yeah. I didn't show you my mechanism, but this could rotate. If it rotated, it would look like what? Like that. Yeah. Well, then this could take the H, put in the double bond, and then when it puts in the double bond, the two groups will be like this. Okay? But this is just rotamers, right? This is an equilibrium. Which one's going to be favored? Syn or
trans.
anti?
Anti.
Right? Now, very often, this may not be included in a mechanism, and it may be kind of glossed over, and you'd be like, how did it go from here to there? Well, I'm giving you the detailed information here. Because it can rotate at that point, because the pi bond is gone. Okay, we'll talk more about stereochemistry and going forward. Okay, summary statement. An E2 requires what? Strong base. An SN2 requires what? Strong nucleophile. Okay, there's no strong base up here. Okay, this is a good old E1. Give that product. That's an good old E1 mechanism. The leaving group turned around and acted as a base. That's how we got HBr. Okay? If you heat this compound and hold pH paper over the condenser, it'll probably start turning red. Why?
It's acidic.
It's generating strong acid. Thermodynamics and entropy of elimination reaction. What about entropy? Let's talk about it. Is this reaction favored by entropy?
Yes.
Yes.
One molecule going to two?
Yes.
Yes. What about thermodynamics? Is this reaction favored by thermodynamics? Calculator.
No.
You can get out your calculator, but what do you
No.
think?
No. Because it requires
Which
heat.
side has the stronger bonds?
Oh.
And just focus on the organic. Which side looks,
The
The
alkene.
which organic has stronger bonds? We had two
Sigma.
sigma bonds here that are gone and replaced by a pi bond. Which is stronger, 2 sigma or a pi?
2 sigma.
2 sigma. Stronger, thus more stable. We actually went to a less stable product. So in terms of thermodynamics, we're making a less stable product. So it's not favored by thermodynamics, but it is favored by entropy. If something is favored by entropy, will heat help?
Yes.
Yes, because in your Gibbs free energy equation, entropy is multiplied by what?
T.
Heat. And so if entropy is good, the more you can add heat and multiply it up, good. Yeah. Heat favors the elimination. Question.
Is it also reasonable to say that it's not thermodynamically favored because you have to put heat into the reaction to get the product?
No.
No?
No. No, because you got to be careful. We can go from here to here. If this is product, it's thermodynamically favored.
It still has to go.
Guess what? You still may have to put heat in. So don't confuse transition state requirement for this is your thermodynamic.
Okay.
Diamond reacting with oxygen is thermodynamically favored. I'm kind of reversing, I think, what you taught. Does that mean that diamonds are all the time reacting with oxygen? No, we wouldn't have diamond rings. I mean, they'd be like oxygen everywhere. Keep it away from oxygen. No, it's because it's got such a high activation energy. You have to put a lot of heat in to then get that favorable outcome. Okay, a lot of that is just sort of review. Okay, let's dig in deeper. What about when isomers are possible? This first reaction up here, if you do a beta elimination, there's only one product possible. Because there's only one beta hydrogen type. And we'll see different types in the next example. Remove that, okay? Basically, you're putting in the double bond between the beta hydrogen and the leading group. The double bond will be here. That's your only choice. The double bond is there. And look at that alkene. Is it stereogenic?
No.
It's also not stereogenic. It's the only possible product we show as an elimination product. But look down here. What if the leading group was on that carbon? Now we have a beta hydrogen here. Because this carbon's alpha. That's beta, but this is also beta. There's also one here. And so we can put the double bond in over here. That would be that, same product as above. But down here, we can also put it in over here. And that would be this. But guess what? This alkene is stereogenic. And it could possibly be the Z product. So in that scenario, there's 3 theoretical products. And we have to figure out which one is going to be formed. And we have enough information to predict that. How are we going to predict?
Find out.
Does everybody understand how there would be 3 possible theoretical products for us? Only one above? Okay, how do you choose? How does this, what do we look at? First, the most substituted alkene is the thermodynamic product. We've known that for 2 months, right? Which alkene is more stable? The one that's most substituted. In the context of these reactions, that's called the Seyssel product. thermodynamically the most stable. Okay? Whenever you eliminate, you use the term Zaitsev product. All right? Now, nobody knows how to spell Zaitsev. Some books spell it with a Z. Zaitsev. Okay? Is it Russian? I think Russian probably. Okay? I spell it with an S. Some people put no Z, some people put one Z. Okay. It's always the major product in an E1. But not necessarily in E2, which can often give the less substituted alkene. The less substituted, which is not the most stable, that one is called the Hoffman product. Have we heard of Hoffman before? No. There's a Hoffman rearrangement, I think you might see there too. Back up here. Of these three, which is the Zaitsev product?
E.
E.
The middle one.
Middle one. S I'm saying for Zaitsev. Now when you read it, it says Zaitsev with a Z. Don't get confused by my S. Okay. S is Zaitsev. That's the Zaitsev part. The middle one. Why? Most substituted alkene. Ah, but hold on. Isn't Z also equally as substituted? They're both disubstituted. So how would we break the tie? Which is more stable, E or Z?
E.
E. So we have something else to use to break the tie. Of the three up there, which is most stable? The middle one. The most stable one is called the Zaitsev product. Okay. Which one's the Hoffman product?
The left one. The left one.
Okay. Yes. The less substituted. The first one is a monosubstituted alkene. There you go. I reckon the third one is neither. Okay. So if the reaction occurred by an E1 mechanism, which would be the product?
The first one.
E1.
Oh, E.
Okay. It says
Middle.
Zaitsev. If this was an E1, it would be the one labeled as S. If it was E2, which would be the product? If this was E2, which would be the product? Not necessarily. It doesn't say that. It says not necessarily the S. It says that E2 can often give the first one. Doesn't say it will. Sometimes H can be formed. Okay? It's straightforward here. E1 gives which one?
Zaitsev.
Zaitsev. E2 gives which one?
Either one.
Possibly the H. It's more open. We have to get more information about it. Okay, example. If you take this alkyl bromide with water, and it probably should say heat, what type of elimination can we do? E1. I don't see a strong base, so you can't do E2. E1. What's going to be the product? Will the double bond be here? Will the double bond be between the carbon with the leaving group and the N carbon, or between the carbon with the leaving group and that carbon? Which alkene?
The more stable one.
More stable one?
The Zaitsev.
This one, yes. Not that one. Pretty straightforward. This should say, when possible. Because in the product shown here, is E and Z possible? No. The product shown is not stereogenic. In the example above, it was. I showed both. And when both are possible, which one is more stable? E, bigger groups opposite. Typically, unless the E to Z terminology was based on, I don't know there's going to be an exception to that. Typically, E is always more stable because the bigger groups, they're always going to be opposite with E. Okay? Why does E1 always give thermodynamic product? Because E1 is thermodynamic conditions. E1 is reversible. It's equilibrium conditions. And maybe we'll mention that more as we go along. But once you achieve those type of conditions, thermodynamics takes over and you typically get the best product. Okay? Let's look at E2. Same alkyl bromide, but now let's use a strong base. If you use hydroxide, it's going to be an E2, concerted, okay, all at once now. You're going to get the same product as with the E1. Thermodynamic product. Say so. But if you use a sterically hindered strong base, which butoxide is because it's got these wings on the carbon. Okay? And it's considered sterically hindered. Now the groups aren't on the oxygen, but they're on the carbon next door. And that does increase the sterics. Okay? And so if this is the nucleophile, over here may not matter, but let's put a lot of stuff over here. Okay? And consider it bigger, like on both sides. All right? And then I'm going to come in here and take the H, and it's like, here I come, and it's like, uh-oh, this kicked me off. Yeah, I could do like this, but that takes more energy and preciseness. As I'm approaching, like, uh-oh, you know, all this stuff over here keeps getting in the way. That's sterics. It can happen over here, and indeed it does. If you use a sterically hindered base, you actually get the Hoffman product as the major product. Why? It all has to do with the H being more accessible. This H is more accessible. This one, if you actually look at it, is hidden between the two methyl groups. And you can look at that closer. So if I'm very hindered, which H am I going to be able to get better? The one that's more accessible. But then you may ask, well, that doesn't lead to the best product. And I would say, I know. But the reason you don't get the best product is because you're using a sterically hindered base. And thus, what can we point to that really gets this? If we do a reaction coordinate diagram, and we start with starting material, if we show the two products, B and C, how would we put them here? Well, neither one of them is as stable as that. So they're both higher, but C would be here, and B would be here. But isn't B more stable than C? Okay. And if we're using this base to get to B, which doesn't happen, it's like, whoa! Very hard. Okay? Crowded, right? We get to C, it's more accessible. It doesn't require as much energy in the transition state, and maybe it's like this. So which reaction is going to be favored here? Or product?
C.
Reaction to give C or reaction to give B?
C.
Reaction to give C will be favored. Okay? That's what we're showing here. Because of the steric crowding, this is one step, right? It's all concerted. There's no intermediate. Don't we go directly from A? Okay? Does this make sense? Yes. And you would say, I'm not getting the most stable product. Transition state's higher to give that. Transition state is lower when the H is more accessible. Is that what it says? Abstraction of less hindered? I think everything is said here. Any questions about that? I'm not going to reread you what is written there, but I think we've covered it. Make sense? Okay. So sterically hindered bases can actually give the Hoffman product. There's another reason you may get the Hoffman product, and that is the stereochemical requirement for an E2 elimination. In an E2 elimination, the leaving group in the beta hydrogen that has been extracted must be coplanar. With anti-coplanar, which is also known as anti-periplanar, very much preferred over syn-coplanar. We'll explain these terms. You already mostly know them. If the Lg and beta hydrogen cannot become anti-periplanar, then beta elimination will be very difficult. As a result, sometimes the less desirable, the less stable Hoffman product is formed because the Lg and beta hydrogen leading to that product could become anti-periplanar, while they could not do so to give the more stable Zaitsev product. This requirement must also be considered if the elimination product will be E or Z. And choosing between E or Z. Note that an E1 mechanism does not have this requirement. Mainly because in an E1, the Lg and H are not removed in the same step. Okay, what do we mean by anti-coplanar? It basically goes back to, remember rotamers? Okay. Two green groups are syn, now they're anti. Okay. This is called syn-coplanar. It's like if they're all both on the board. If the plane is right through here. Okay. All right. They're both sitting on the plane of the paper, and they're syn-coplanar. If we rotate it, everybody agree they're now anti, but they're also anti-coplanar because they're both on the plane of the paper. Okay. We could have used those terms 2 months ago. What about that? Are the two green groups coplanar?
No.
No, if I have a piece of paper here, that one's in the plane, but the green one over here is facing forward, out of the plane. Okay? How do we show this? Remember Newman projections? Circle, circle, dot, dot? All right. Br and the H, let's consider Br and H both green. We're kind of drawn anti-coplanar here. Are they really? What's another way to do it? What if we drew it like this, and then put the bromine in the front, straight up, and the H in the back, straight down? Yeah. And then the plane is, that's the plane. They're both on that plane, and one is up and one's down. That's anti-coplanar, with a dihedral angle of 180 between the two groups. 90% of this you've seen, we're just using new terminology. Syn-coplanar, but also rings. We'll do a lot of rings. Which H is anti-coplanar to the bromine? Well, only that one. Okay? If we make the bromine red, And let's put a chair conformation, yeah? Bromine red. Let's look at the beta carbon with 2 H's on it. Which H is anti-coplanar to the bromine?
The bottom one.
It's only that one. This one is sticking out like this. Okay? Look at it here. See the plane? That one's up and this one's down. Okay? Okay. There's the plane. Bromine's up. This H is down. This other one is not in the plane, and it's also not anti. Let's do a ring flip. Now the bromine became equatorial. Now let's look at the adjacent H's. I can still hold it like this. It's equatorial, but I can still look at it like this. Which H is anti-coplanar to the bromine?
Neither. Neither.
Neither. A take-home here is, to have an H anti-coplanar, the bromine has to be axial or equatorial?
Axial.
It has to be axial. Same thing I showed you here. It has to be axial. One of them will be anti-coplanar. If the bromine is equatorial, neither of the beta hydrogens on either side are anti-coplanar. Take home, the leaving group in a ring like this has to be axial when the elimination takes place. Let me ask you this, is axial the favored position for a big bromine?
No, equatorial is better
No.
for larger groups.
So it actually has to be in the less favorable position for the elimination to take place. Keep that in mind. We'll look at examples of these. Show expected product for each reaction. We'll do this on Monday. Please look at it. We're going to be doing Newman projections. I would recommend Newman projections and rotating it to put the leaving group and the H anticoplanar. But you also got to think about Satsef and Hoffman. Base. Is KOH a sterically hindered base? No. KOH is one of the smallest bases you can have. How about this? Does that look like a sterically hindered base? See some of you in lab upstairs. We'll get going at 2:30 upstairs. Have a good day, guys.